Please welcome Kush Singh. He recently learned the difference between an acronym and an initialism.
Yes.
Today he will present how to do a proof with WOP.
It's just called WOP.
WOP. It's also something you don't understand.
Well, I set up, I'm going to answer the burning question in all of your minds right now. What's the difference between an acronym and an initialism? Well, you see, an acronym is when you have words such as, or a phrase such as the central, well, that's a bad example, such as the National Space Aeronautics Association, and when you take the first letter of each word, and you put it together, and you pronounce it as a one word. So in this case, you pronounce it NASA, and that's an acronym because you pronounce it as a word. Similarly, if you have the well-ordered principle, you would pronounce it as WOP instead of WOP. And an initialism is where you have the words, like the Central Intelligence Agency, but you pronounce the letters instead, so you call it CIA versus CIA, or NSA instead of NISA. So, but then I digress. So today I'm going to be talking about the well-ordered principle, which is a method of a technique which can be used to prove things in number theory. But before I get there, let me go over a few things first. First, I'm going to tell you guys about a set. In mathematics, and more specifically number theory, a set of numbers is basically a fancy way of saying you take a collection of numbers, and it can be as many or as few numbers as you want. You can take 1, 2, 4, 3, 9, 275,374,236, or you can have no numbers at all. Or you can have infinite numbers from negative infinity to positive infinity. So a set is just a fancy way of saying collection. And the way the well-ordered principle works is, it states that every set of non-negative integers must have a lowest element, which means if you have a set of numbers, there's always going to be a smallest one. So if you took the set of ages of everybody in the audience right now, the least element by the well-ordered principle would probably be May's age, just as an example. So let's use well-ordered principle to be able to prove an interesting property of numbers, but it won't be too advanced. So to get started, does anybody know what the sum of numbers from 1 through 10 is? 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus so on and so forth? Someone will do it really quickly. I'll put it up on the board. Promote? 55. Okay, good. So, but how would you sum numbers from 1 to 100 if you don't know the technique? So let's take a look. And this actually brings an interesting story with it, which I'll bring up after this. So obviously this is a very daunting sum to be able to do by hand, and this is exactly why the teacher of a young Carl Friedrich Gauss, which was one of the greatest mathematicians of the 20th century, assigned him to do this problem in first grade to keep him and the rest of his class busy, so that the teacher would have a little bit more time to prepare and get some peace and quiet. So you can imagine the teacher's surprise when the young Gauss was able to pronounce the sum correctly as 5,050. But how do you do this? Well, he clearly didn't just add them up manually. That would take quite a long time. So let me show you how he managed to go about finding the sum. So let us say that this sum is equal to the term s, just for short. S. And let's just add s to s to get 2s. So 2s is equal to this is 1s, and we need to add another s to it to be able to get the 2s. But instead of writing it in 1, 2, 3, plus 98, 99, 100, let's write it backwards, because when you're adding a sum, it doesn't matter in which order you do it. So let's just see what happens. And if we start adding this up, you'll see something very interesting. So 2 times the sum is equal to 101 added together 100 times, because there are 100 pairs we're adding up here. So this is equal to 101 times 100. But if we only have 1 times the sum, you want to divide this by 2. So you get math, you can see this is equal to exactly 5,050. But say you want to do the sum of numbers from 1 to a million, or 1 to 234,868 and 0.24. Bad example, but so how can we generalize this is what I was trying to get at. So well, the way you do that is, with the you can use the well-ordered principle to prove that the generalized formula, which in this case is so what this is saying is the sum of numbers from 1 to n is equal to n times n plus 1 divided by 2. So how are we going to show this? And today I'm going to use a proof by contradiction, which basically says you assume that the opposite is true and try to do it backwards and show that the opposite is false, thus showing that the negation of the opposite, which is this statement, is true. So since we want to use the well-ordered principle, let us define a set. So let set S we're going to let set S equal the set of all numbers where this formula does not work. Okay, so a few quick things before we move on. This symbol, WTS, says want to show, and we're trying to prove this statement. And this statement here is set notation, where we show that for all n, which is a non-negative integer, integers are just the numbers 0, 1, 2, 3, and so on. And also negatives, but in this case we're only looking at the non-negatives, so just these. And so n is one of these numbers where the sum of the numbers from 1 to n is not equal to n plus 1 over 2. So this is the set of numbers where this proof does not hold. And we want to show that this set is empty. And we want to do it by contradiction, so we're going to assume that this set is not empty and then show that it is empty because the well-ordered principle does not hold. So how are we going to do this? Let us assume so we're assuming S is not empty, or S is not a null set. This means that the well-ordered principle applies, and that therefore and this is saying, by the well-ordered principle, there exists an element E and the non-negative integers, such that E is an element of this set S, if we assume that this set is not empty. So, let's take one base case to show why E cannot be equal to 0. So the sum of numbers from 1 to 0 is always equal to 0 because you're not adding any numbers together whatsoever. And that is equal to 0 times 1 divided by 2, which means that 0 fulfills this property and that 0 cannot be an S. So that means that E has to be greater than 0. So what can we do with this information? And so, let me just erase a little bit. Since E is greater than 0, and E is the smallest element in set S, that means E minus 1 is greater than or equal to 0, and it is also not in set S. What does this mean? So, this means that E minus 1 follows this property. And that means that, if we write this out in the expanded form, product of numbers from 1 to e minus 1 is equal to e minus 1 times e minus 1 plus 1, which is just equal to e divided by 2. But since this is an expression of equality, we can add e to both sides. And this should be plus, obviously. Okay. So we add e to both sides. And now we have e plus 1 plus 2 plus 3 plus 4 plus e plus 1. So this is all numbers from 1 to e is equal to e times e minus 1 plus e by 2. And this can be factored as e into e plus 1 over 2, which means that e fulfills this property. And since e is the least element in the set, and it fulfills this property, that means it is not in the set, which means that the set has to be empty, because if the lowest element is not in the set, then we have to kick it out, and then we have the next lowest element, and that can also not be in the set. So and that has to be kicked out, and we can use this to show that there can be no elements in E in the set S because there's no lowest element in the set. And therefore, our original assumption of S being non-empty is false, and that the set actually has to be empty, which shows that our original statement that we wanted to prove is true. Ergo, we've proven it using the well-ordered principle. And now we can write QED, which is demonstrative, which is Latin for saying to be proven, which states that we have proven our original supposition by using the well-ordered principle. Thank you.